Thank you all for coming today. So it's a great pleasure to be here. This is my very first time at Stony Brook. I had the chance to give one Zoom talk here last year, but it's my first time in person, and it's been a really nice visit so far. So thanks a lot. Okay, so today I want to talk about the notion of quantitative stability in the calculus of variations. So stability is a notion, okay, as Claude was pointing out, that we use in various ways throughout mathematics. We also use this in plain English to talk about a building being stable or a chemical compound being stable, to mean if you perturb things a little bit, the building or the chemical compound doesn't change too much. It somehow stays near its ground state. And we'll be using the word stability in the same way. We'll want to understand this in a quantitative sense. When you perturb a minimizer of some energy functional, how far it can move away from the ground state. So maybe two themes to keep in mind throughout the talk. The first one is that we'll see various different quantitative stability estimates in a couple of different settings. And a lot of times the statements look kind of similar, and we'll draw the same picture a couple of different times. But something that makes this a rich field of mathematical study is that there's not really a one-size-fits-all approach to these problems. So different settings call for the development of new techniques and ad hoc methods tailored to the setting at hand. And the second thing to keep in mind is that these kind of estimates are interesting to study from the standpoint of the calculus of variations, but people also tend to care about them because they tend to be useful in a variety of different settings. So we'll see a couple of applications throughout this talk too. Okay, so I want to start in a very classical setting, dating back to the ancient Greeks, which is the isoparametric problem. So the isoparametric problem says if we look at all subsets omega of Euclidean space. So here you can think of omega as like an open set, a bounded open set with smooth boundary. If we look at all such sets in Euclidean space that have some fixed volume, then balls are the sets that have the smallest perimeter. Okay? So here when I say volume, I mean an n-dimensional volume, sort of the filled in region here. And you can think for a smooth set, the perimeter is like the n-1 dimensional surface measure of the boundary. And we see the isoparametric problem showing up in the real world. So for example, this is the mathematical reason behind why soap bubbles take a round shape, because the soap film has surface tension. And so the energy minimizing state is the one that minimizes the total surface area subject to a fixed volume of air trapped inside of the bubble. So mathematically, we can formulate the isoparametric problem. Excuse me, just this. Okay. We can formulate the isoparametric problem as a minimization problem in the following way. So we want to minimize the perimeter. I'll denote this by P of omega, the perimeter of a set omega, subject to a constraint. The constraint that the volume is some fixed number. Since we're in Euclidean space, we can always normalize this to be 1. This is because Euclidean space looks the same if I dilate it, if I zoom in or out. And so the fact that balls minimize the perimeter is saying that the minimum value of the perimeter among such sets is equal to the perimeter of the ball. Okay? So just a little bit of jargon I'll introduce for later on in the talk. We'll see a bunch of different energy functionals. The perimeter is one example in an energy functional. An energy functional will be something that takes in an object like a set or like a function and gives back a number, and typically we want to minimize these quantities. So the basic problem of stability is the following. In this setting, if I have some set omega, and I know that the perimeter is almost minimal, it's not quite equal to that of the ball, but almost, then does this force omega to be close to a ball in some geometrically meaningful sense? And we'll want to understand this in a quantitative sense. Okay. So in the context of the isoparametric problem, this question was answered in a complete quantitative sense in the plane, in 2 dimensions, by Bonnison almost a century ago, in 1924. And then it took quite a long time later until the higher dimensional analog of this theorem was proven. So this was proven by Fusco, Maggi, and Pertelli in 2008. And the theorem says the following. So take any subset omega in Euclidean space. Again, think bounded open set with a nice boundary, normalized to have volume 1. If the perimeter of this set is equal to the perimeter of a ball plus epsilon, you can think epsilon can be big or small, but the theorem is interesting when epsilon is small. Then the distance between omega and the nearest ball of volume 1 is at most of order epsilon to the power 1/2. Okay? And this order 1/2 growth rate is optimal. So okay, how can we think about this kind of theorem? Let me give you guys two interpretations, two ways to think about this. So the first interpretation is the following. So you can think about injecting epsilon amount of energy into the ground state. So going back to this real life instance of the isoparametric inequality, if we think about our ball being the area or the region enclosed by a soap film at rest, if you inject energy, say you put this soap film, this bubble beneath a Bunsen burner in your lab, and so the molecules start moving around, things get agitated. Then if you inject epsilon amount of energy, what this theorem of Fusco-Maggi and Pertelli says is that the resulting shape is deformed. Say it looks like this, you've added an epsilon amount of energy. It's deformed by the ground state by a distance that's at most epsilon to the power 1/2. Okay, and well now it looks...
In terms of physical model, heating it is a bad idea because you'd probably change its volume, right? You'd increase the pressure inside, so... But anyway, yeah.
Yes. Okay. So fine. So that you make a fine point that perhaps this is not the best, most physically accurate way in which you could...
Just take a step back and look, and then it'll shrink again. You can renormalize it. It's okay.
Okay, maybe you can think there's a small earthquake, right? So I just want to agitate the shape a little bit. So, okay, in this picture, it appears that the rendering of my slides here has lost something, but so the distance here is measured in the following way. Let me just redraw this picture. So here if I've taken my set first, I first translate my set to find the ball that has the maximum possible overlap with my set. And the way in which this distance is measured is it's the volume of the symmetric difference. So it's the volume of the set of points that are in the ball and not in my set of omega, union those in omega, not in the ball. Okay, so the volume of this blue set is at most order epsilon to the power 1/2. Okay, so here's a second way that you can interpret this result I told you about of Fusco-Maggi and Pertelli. We can view this as a statement about the energy profile of the perimeter functional. Okay, so I've restated the result here, replacing epsilon by epsilon squared. Okay, so just changing the symbol, right? But so now it says if I have some set whose perimeter is equal to the perimeter of the ball plus epsilon squared, then the distance is at most of order epsilon. So what this is saying is if we draw this kind of schematic picture, where here on this two-dimensional axis, I'm representing the space of all subsets of Euclidean space with volume 1. So this is an infinite dimensional space. And here along this axis, I'm representing translations of balls. These are our minimizers. Okay, so this is a finite dimensional space. It's n-dimensional because I have n dimensions of translations. So what we already know from the isoparametric inequality is that this energy functional, it's minimized along this axis of balls. And what this quantitative stability estimate says is the energy profile grows at least quadratically as you move away from this space of minimizers. Okay? Quadratically, and here in this schematic picture, this distance here will be in terms of the distance measured by the symmetric difference to a ball. The volume.
It's really a measure of the symmetric difference. So when people see this expression distance between the two, they might think you're talking about maybe it's contained in a collar. And of course, as this example shows, you could put extra connected components in to be very far away without.
Yeah, that's a nice point. So right. So maybe I'll mention that. So right, but this distance. Okay. So maybe not to just draw things, but by distance here, I mean, okay. First of all, I have taken the optimal translation. So I'm considering B to be the ball that has the maximal overlap, but this is really just measured in a volume sense, in the volume of the symmetric difference. Now, you might hope to say, okay, could I prove a better result in which I control not only the volume of the symmetric difference, but maybe the Hausdorff distance between the boundaries or something? And as you point out, the answer there is no. This has to do with how the perimeter behaves. You could have a disconnected component and send it very far away. Or even if you want to study connected sets, as soon as you're in dimension 3 or higher, you can add on a long, thin tentacle to your set and pay very, very little in the perimeter, but make the Hausdorff distance between the boundary of your set and the boundary of the ball as large as you like. Okay, so, and actually while I'm here, this is also a nice moment to mention why here we see the power epsilon to the power 1/2, or rewritten in this way, we see, when we want an epsilon here, we see epsilon to the power 2. Sort of heuristically speaking, you can think about if I take a set omega and I do a Taylor expansion of the perimeter around the ball, okay? So what I'm going to write, you can actually make this rigorous in the right sense, but let me just kind of state this in a heuristic way for now. If I think of Taylor expanding this around the ball, then at order 0 in my Taylor expansion, I get the perimeter of a ball. At first order, I see the first derivative, or the first variation, okay? Plus, then I see 1/2 times the second derivative, or what's called the second variation when you're looking at energy functionals, plus higher order terms. Well, this is the first variation evaluated at the ball. The ball is a minimizer of this perimeter. In particular, it's also a critical point. So this Taylor expansion will vanish at first order because I'm Taylor expanding at a critical point. And similarly, this ball is a minimizer, so I expect the second derivative to be at least non-negative. Okay? And so in the case of this isoparametric problem, the second derivative is actually strictly positive, at least in the directions that don't correspond to translating to another ball, which is why we see this Taylor expansion showing up at order 2. Okay, so this quadratic separation corresponds to seeing this Taylor expansion starting at order 2. Okay, so more general framework. So we've seen the specific example of the isoparametric inequality. So more generally, given some energy functional, for example, yeah.
So when you write out the first and second variations, I assume that you actually are restricting to the set of changes of the domain, so that it's actually things like you have a graph over the boundary of some normal vector field, right?
Yes. So that's exactly the setting in which you can make this sort of vague heuristic rigorous. Is if you're considering sets whose boundaries are parameterized by a graph of a small C1 function over the boundary. And then, there are various different proofs of this quantitative stability, but one such proof does go sort of a penalization argument based on regularity theory allows you to eventually reduce down to proving stability in this case, at which point you can run this sort of Taylor expansion argument, use facts that you know about spherical harmonics, eigenfunctions of the Laplacian on the sphere, to really just prove this by hand. Let's say a big part of the challenge is going from proving a statement about all sets to just having to prove a statement about these sets. Okay, any other questions?
I guess I was actually expecting you to say how it's related to that. Because here you're just saying that there's some epsilon perturbation. You get the area changing by epsilon squared. But then the distance, what is the distance somehow, I guess it's because it's the volume of the missing pieces. You're saying those are bigger and they're epsilon. So I don't see the connection between the epsilon and the epsilon squared in this case.
Okay, maybe you should think, you should think, this is a major quote, but if you think omega is equal to the ball plus an epsilon perturbation. And the sense in which this is not actually nonsense is precisely in a setting like this where you can really say, well, let me consider a set omega whose boundary, omega, can be written as 1 plus epsilon u of x for a function u times x. That's the normal. So my boundary is parameterized by going x to a point on the boundary of the ball, pushing in a direction, pushing in a magnitude specified by this function u. U is positive here, negative here. Okay, here I really can. I mean, this is a sense in which it makes sense to say, okay, my domain is like a ball plus an epsilon perturbation. Then you should think in the Taylor expansion, this is order 0 in epsilon. This one's order 1 in epsilon. And this one is order 2 in epsilon. So this term is going to be, honestly, this term, when you write it out, this one is equal to epsilon squared times an integral quantity involving the first order derivatives of u. Okay. So does it make sense? So this is sort of, if we're thinking u is order 1, then this is why.
Yeah, but what you have, I mean, you have to say that this epsilon is the volume of this, which I don't.
Not quite. Okay, so in this context, you.
Right? It's the symmetric difference. You said that.
Yes. Okay, so in this case, for a set like this, then if we ask that say the C1 norm of u is order 1, then epsilon is going to be roughly right. So epsilon times the C1 norm of u, or even the L2 norm of u, this is going to be approximately, and this will actually control the symmetric difference between omega epsilon
If you just
and a ball.
The volume of that region, then it has a Taylor series it has a Taylor series expansion too, and you might have thought, well, you're looking at dimension n, so there's some power of n, but it's like 1 plus epsilon to the power n. It looks like 1 plus n epsilon plus other stuff, right? So you won't see.
So that's what I was saying.
Yeah,
that
yeah.
The volume of that piece is
Right.
epsilon.
Yes, the volume. Sorry, I understand your question now. The volume of this symmetric difference will be of order epsilon.
Okay, that's fine. Sorry to distract.
Oh no, thank you for your questions. So okay. So more generally, we'll be looking at different energy functionals and talking about the question of quantitative stability. So this is describing the behavior of low energy configurations, not quite at the ground state, but almost. And we'll keep with us these two perspectives. One, we can think about injecting some epsilon amount of energy into the ground state and trying to understand quantitatively how much the resulting object can deform from the ground state. And the second perspective we'll keep with us is that this is a statement about the energy profile, how much the energy has to grow as we move away from the space of minimizers of this energy functional. Okay, wow. Okay. I've been talking for a long time already. Okay, so why do we care about these things? So I mentioned to you that there are applications that motivate these things, and it's kind of neat to see a couple of different areas where quantitative stability estimates are actually useful. So one way that quantitative stability estimates can be useful is to understand the ground states for more complicated energy functionals. So the perimeter functional is kind of simple, and we can understand that balls are the minimizers of the perimeter using symmetrization arguments. But this really has to do with the fact that the perimeter is a functional that doesn't see rotations. For more complicated types of energy functionals, it can be difficult to classify the ground states. So, for instance, some work that I did in my PhD thesis established some quantitative stability estimates for energy functionals that arise in crystallography. And later, in joint work with Rustam Chokshi and Ihsan Topaloglu, we applied these quantitative estimates in order to explicitly characterize the ground states for a more complicated energy functional, which was a variant of the so-called liquid drop model in nuclear physics. Okay. Another type of application of these quantitative stability estimates is to effectively approximate other variational problems. So there's a really nice example of this in work of Garcia Trios, Murray, and Thorpe, where they consider a clustering method in data science for finite data sets that are sampled from a distribution on some continuous domain. Okay? And here they apply a quantitative stability estimate for the isoparametric problem, this time on manifolds, and they use this to prove high probability rates of convergence for the clusters that are formed from these finite data sets. As they send the number of sampled points to infinity, high probability convergence to actually the clusters that are formed by studying an isoparametric problem on the continuous domain. A third type of application is these things can be used for studying rates of convergence for flows. So there's some nice work of Carlin and Figali in which they consider quantitative stability for a Sobolev type energy. We'll see a different Sobolev type energy in a little bit. And they apply this to prove convergence rates for a model called the Keller-Siegel equation. This is something that models population density of bacteria over time. Okay, so today in this talk I want to show you 3 different settings in which we have some quantitative stability estimates. In the final one, some applications too. So this will be the Sobolev energy functional. Next, the Yamabe energy functional. And finally, for the energy functional, which is the first eigenvalue of the Laplacian on domains. Okay, so let me start with the Sobolev energy functional. Okay, so whereas before in the isoparametric problem, our objects were sets, open sets in Euclidean space, now the objects we'll consider are smooth functions, so U from Rn to R, that have suitable decay at infinity. Okay, we'll also have a parameter P that's between 1 and the dimension that's going to be fixed. And the Sobolev energy functional, then, we'll write it E sub P of U, is defined in the following way. We take the gradient of this function U, we take its modulus to the power P, and we integrate that. Okay? So you can think of this as some measure of the energy of your function. If your function vanishes at infinity, as we're asking, or decays at infinity, and it has 0 energy, then it has to be just the constant 0 function. It costs some energy for this function to separate from 0. And tuning this parameter between 1 and n just changes whether you want to place more emphasis on regions where the derivative of u is, say, very big on a small set, or where it's pretty big on a large set.
So you're not, the decaying at infinity is different from just finiteness of the Sobolev P norm?
Oh, yeah.
No, I'm asking what she's requiring. I know that they're different.
Yeah.
Right. So, bless you. So we can say something more generally. I will not need the finiteness of the LP norm. Okay, I want objects in the homogeneous W1P space, so they should have finite LP star norm, where this is the dual norm. But really, actually, this will be implied if your starting point is that you ask for, say, the measure of the superlevel sets to be decaying. But right, so I don't need these actually in. If you want, this is the take functions that are in the completion of the homogeneous W1P Sobolev norm, the completion of C0 infinity. Okay, so as we did for the isoparametric problem, we can formulate a minimization problem for this energy functional. So we'll minimize this energy. Again, P is just fixed. Now among functions that satisfy the analogous thing to our volume constraint before, which takes the following form. We'll ask that if we take take the absolute value of u, take it to a power p star. It's a power depending on n and p, and we integrate. We want this to integrate to 1. Okay, so this power p star, it's governed by the scaling of the problem. Scaling basically tells you there's exactly one value of p star you could put here, so that this is a meaningful volume constraint, and so that this minimum value is not 0. Okay, with this, the minimum value is actually equal to the energy of a certain profile. The energy of a function v, where v is what I'll call an invariant scaling of v naught. So let me explain this by picture. So let v naught be this blue function it's radially symmetric, polynomially decreasing, not compactly supported. We could write it down explicitly, but it's probably not that informative. But it's one fixed profile. And then a couple of symmetries of this function automatically have the same energy as v naught. That if we translate this v naught, it's going to have the same energy and the same size constraint. And similarly, if we dilate this, if we squeeze this profile or stretch it, it'll have the same energy. So once I tell you v naught is a minimizer here, then also its invariant scalings are, and these are all of them. These are all of the minimizers.
So your constraint here only involves the function and not its derivative. But the energy you're looking at is what Sobolev L.
That's right, exactly. So I'm fixing the volume, I'm fixing this LP star norm, I'm minimizing just the energy term.
It's just the
so
it's not the Sobolev norm. There's not also the LP.
It's the semi-norm. It's just the gradient. So if you like this number, if you call it S, or if you call it C, this is your optimal constant in the standard Sobolev inequality on Euclidean space that says gradient U in LP is greater than or equal to constant times U in LP star. Yes?
Does the profile V depend on the choice of P?
Yes, it does. It does depend on P. So yes, it's like 1 plus modulus x to the P prime, that's the Holder conjugate, to the minus n minus P over P. Okay, as I told you, I don't think maybe until you are doing computations, there's nothing really to be gained except for it depends on P, decays polynomially. But yes, but it does depend on P. Okay, so quantitative stability for this Sobolev energy. So this was something that was conjectured by Brazis and Lieb back in the 80s. And in the special case when P is equal to 2, the conjecture was proven just a few years later by Bianchi and Egnell. Okay, so what they proved was the following. Take any function u from Rn to R, again with suitable decay at infinity, and normalized so this volume constraint is equal to 1. Then if the Sobolev 2 energy is equal to that of the minimizer plus epsilon, then the distance of u to the nearest invariant scaling of this minimizer v naught is at most of order epsilon to the power 1/2. Okay. So then it was quite a while later until any results were generalized beyond p equals 2. And sort of what you should think about the big difference between p equals 2 and p not equal 2 is when you tune this p parameter exactly to 2, the Sobolev energy is a bilinear form. So you have some underlying linearity to the problem that as soon as you tune that parameter away from 2, you lose. Okay. So then some years later, for the range p between 2 and n, by Figali and myself, and then later for the full range p between 1 and n by myself, we proved the following. So the analogous type of result, if you take some function u from Rn to R, satisfying this volume constraint or this size constraint, if the Sobolev p energy is equal to that of a minimizer, the minimizer plus epsilon, then the distance between u and v is at most order epsilon to a power, bless you, 1 over alpha. Okay, so in these results, alpha was some explicit power, so we have some explicit quantitative control, but was not optimal. And then in a really recent nice Duke paper, Figali and Zhang improved this result and established the optimal exponent here. So alpha, this optimal exponent is the maximum between 2 and p.
So the distance here is measured in terms of the p star norm of?
The LP norm of the gradient. So, okay, so nice. This brings us to the next slide, although I had some, okay, so all of the highlighter stuff seems to not be rendering here. But yes, so it's a nice question. So in terms of this distance or how we can interpret this, you can think we start at some ground state, we inject epsilon amount of energy into our ground state. So our resulting function is this u. Then if we look at the closest, minimizing profile v, then this distance is, okay, to the specialists in the room, the distance is the homogeneous W1P norm of u minus v. To the non-specialist, I guess the important thing here is that if this is the nearest profile and this is my other function, u, then this notion of distance, it controls the size of u minus v in some integral sense, but it also controls the oscillation of this function relative to the oscillation of v. And this is in the form of the gradient of u minus v to a power n integrated.
So the optimal solutions here are always just radial functions?
That's right. So the optimal functions here are this profile plus its translations and dilations, and those are all of them. And so, right, so this says quantitatively, if you have low energy, you have to look in a W1P sense close to a scaling of this function. Okay, and so the second interpretation, again, it's a similar picture to the one that we saw before. If here on this two-dimensional axis, we represent the infinite dimensional space of smooth functions that have size 1, this integral constraint. And on this axis, we put the invariant scalings of our minimizer. So this is our entire family of minimizers. Then, as this just the minimality tells us, the energy is minimized along this axis. And what this quantitative estimate gives us is an explicit modulus of growth of the energy profile as we move away from this space of minimizers.
Maybe a silly question. Is this invariant? An invariance just of the minimizers or of the entire functional?
Of the entire functional. That's a nice question. So yeah, so you take any function, you take this function, if you just translate it, meaning translation's fine, also the dilations. The entire energy functional is invariant. So the energy of this function and the energy if I squeeze it by a dilation, they're the same. So the whole problem, if you like, yeah, in that sense, like one slice of this picture tells you the whole story. Okay, great. Any other questions?
What happens if p approaches n? Yeah.
As p approaches n. Okay, so let's see. In terms of the embedding, so W1, in the case when p is equal to n, you have a couple of different, you have the embedding into functions of bounded mean oscillation. You also have something called the Moser-Trudinger inequality, which is a Sobolev type inequality, but that takes a different form than these ones. In terms of, so you might hope to say, in terms of these quantitative estimates, can I learn anything interesting if I send p to n in these estimates? And here the constants depend on p and in a completely non-explicit way. So all of these arguments are based on compactness. And so here when I write
everything is a proof by contradiction.
Everything is a proof by contradiction. Now I'll mention there's some very interesting recent work in the case p equals 2 by several authors, Dolbeau, Rupert Frank. There's a recent paper that was put on the archive in which in the case p equals 2, they're able to get an explicit constant right in the, they're really able to say the distance is at most some explicit constant they can write down, epsilon to the power 1/2. But apart from that really recent and specialized to p equals 2 case, all of these are compactness arguments, so you do not get an explicit constant. Okay, so let me mention a second setting in which we can discuss the question of quantitative stability, and that's the Yamabe energy functional. Okay, so the basic setting here is now the following. Let's take a Riemannian manifold that's compact without boundary. Okay, so it's a topological manifold on which I have a Riemannian metric. This gives me notions of things like lengths of curves, curvature, volumes. Okay. So,
where the dimension is definitely bigger than 2, after the depiction.
Sorry?
But the dimension is definitely bigger than 2.
The dimension's going to be bigger than 2. So I'll say one quick word about dimension 2, in which yes, things are. But so yes, exactly. So we're going to be in 95% of this discussion taking dimension 3 or greater. Okay. Really a quick word about conformal geometry. So I say that a metric g tilde is conformal to the metric g if g tilde differs from g by just multiplying by a smooth positive function. For some reasons we'll see down below, it's convenient to write this smooth positive function as a different smooth positive function to a power. Okay, since you're just multiplying by a function, this means a conformal metric will stretch the lengths of tangent vectors, but preserve angles between tangent vectors. Okay? And some notation that we'll use, we'll write g tilde is in bracket g if it's conformal to g. That is, it's in the equivalence class of conformal metrics to g. Okay? Kind of a general goal within conformal geometry is that one wants to find a good representative of a metric within its conformal class. Okay, and in 2 dimensions, we have a very good way to do this, which is the uniformization theorem, which tells us that we can always find a conformal metric of constant curvature. In 2 dimensions, this is the Gauss curvature. It's our only intrinsic notion of curvature. In higher dimensions, curvature becomes more complicated. Okay? And so one analog of this question in higher dimensions is what's known as the Yamabe problem, which asks, is there a conformal metric in a given conformal class that has constant scalar curvature? Okay? So I won't define for you the scalar curvature, but it's called scalar curvature because it's scalar valued. So at each point on my manifold, the scalar curvature is a number, which tells me essentially on average how much the metric is curved at that point. Okay, and we'll use the notation R sub g to denote the scalar curvature. Okay, so this problem has a variational formulation. So this is where what I'll call the Yamabe energy functional comes into play. So we can write, so the Yamabe energy of a function u is given by the integral of the gradient of u squared plus the scalar curvature times u squared. So notice if M is Euclidean space, then this is exactly our P equals 2 Sobolev energy. The scalar curvature on Euclidean space is 0, so this term vanishes, and it's just exactly what we had as the P equals 2 Sobolev energy. Okay? This is a geometrically meaningful functional. If we let g tilde be the metric whose the conformal metric with conformal factor u to this dimensional power, then exactly what this is the integral over M of the scalar curvature with respect to g tilde integrated with the volume form of respect to g tilde. Okay, so this is called the Einstein-Hilbert action functional, and this shows up in general relativity. Okay, and so variationally, the Yamabe problem is the following. So given a metric g tilde in a conformal class G, the metric, the scalar curvature of g tilde is constant, and we can always normalize g tilde so that the volume of the whole manifold is 1. This is our goal, is to find such a metric. If and only if the corresponding conformal factor is a positive critical point of this energy functional, among functions, okay, it's normalized to have this same size constraint that we saw before. And it should be a critical point among functions all satisfying this size constraint. Okay. So this is a very beautiful problem with a beautiful history. The combined works of Yamabe, Trudinger, Oban, and Shane over the course of about a quarter century showed that a minimizer of this energy functional, this Yamabe energy functional, subject to the necessary size constraint, a minimizer exists. And so a minimizer in particular then is a critical point of this energy functional. And so thanks to this variational formulation we gave, the critical point we find as a minimizer here is going to give us a constant scalar curvature metric. Okay, so an immediate consequence of this theorem is that any compact manifold without boundary admits a conformal metric G bar with constant scalar curvature in volume 1, according to my normalization. So we'll call any such minimizer G bar a minimizing Yamabe metric. Okay, so the way I've set this up, it has volume 1. The scalar curvature is constant, and the constant that it's equal to is just the minimum of this either Yamabe energy or the total scalar curvature among volume 1 metrics within the conformal class.
Does it matter if it's orientable or not?
No.
No.
So that when you write devol,
It would just be the volume measure.
the volume.
Just the volume measure. Yeah.
It's great. You have somebody answering your question. Also.
Sorry.
Okay, so in joint work with Max Engelstein and Lucas Polor, we look at quantitative stability for this Yamabe energy functional. Okay, so we prove the following. So let MG be, okay, closed is just a word for compact without boundary. Suppose you have some metric G tilde within a conformal class, the conformal class G, normalized to have volume 1. And suppose that the total scalar curvature is equal to, okay, the minimum it could possibly be plus epsilon. Or phrased in terms of the Yamabe energy, this would be, suppose the corresponding conformal factor has Yamabe energy equal to the minimum plus epsilon. Okay, then the distance of your metric G and the nearest minimizing Yamabe metric, this constant scalar curvature metric, is at most of order epsilon to a power 1 over 2 plus gamma. Okay, so gamma here is a non-negative number, and it's equal to 0 for most conformal classes. So generically, this is equal to 0. Okay, I'll draw some picture and go through our interpretations in the next slide, but you might be unhappy about this gamma and think we should have just worked a little bit harder to prove the same kind of quadratic growth estimate that we've seen in the other problems. But in fact, this is actually needed. So there are actually examples in which the growth of the energy functional away from the minimizers is strictly worse than quadratic. Okay, but generically, for generic conformal classes, we get quadratic, or the estimate distance at most 1 over epsilon to the power 1/2.
Gamma bounded?
Sorry?
Gamma bounded?
So gamma is a finite number that depends on the conformal class. But gamma is not bounded, say, you can't say gamma is at most 100 for any conformal class. It's not.
Quantity that's associated to a given.
Sorry? Well,
Is it explicit?
It's not explicit. It's not explicit. So to each conformal class, there exists a gamma.
Know that it's unbounded? Is it known to be unbounded or not known?
You know what?
I'm wondering if this constant could go to 0, I think.
Yes. So,
It can go to infinity.
Gamma goes to infinity.
yes. For different conformal classes. So actually, that's a nice question that I don't know for sure the answer off the top of my head, but I have a feeling that the answer is yes, and I have one parameter family of examples that I suspect. Oh, I suspect would actually give you gamma going to plus infinity, but okay, but this is not something that I know. So this is.
But is it like the best constant of arising in a certain?
So the way that this arises in our proof is the application of a Wojciech inequality, which really comes from analyticity of the energy functional, and really is like an abstract fact that says there exists a gamma, but sort of philosophically. So you should think so. The example, which really goes back to Rick Shane, which shows that actually this gamma needs to be positive in certain conformal classes, is the example of taking the round metric on Sn minus 1 cross an S1 of a certain radius, equipped with the standard product metric on these two. So you can vary this parameter r, and for r really small, the standard metric is the unique minimizing Yamabe metric, and it's strictly stable. So for r small, you actually get quadratic growth. And then as you increase this parameter r, okay, at some point there's a bifurcation, and you have, for r larger than this, say r naught, you get two solutions, two minimizing Yamabe metrics. At this bifurcation point, at this very largest r for which you have one minimizing Yamabe metric, it's degenerate. So the growth is actually strictly worse than quadratic. And actually, in a really nice recent paper following our work, Rupert Frank showed that for that example, the energy growth is quartic. It grows like power 4 in the distance. But so when I say speculatively, but again, this is not a, if one wanted to try to construct a family of conformal classes with gamma going to infinity, I think the way to do this would be to keep increasing this r, and you get more and more bifurcation points. And it's possible, but I'm not sure that maybe you would get the energy functional vanishing to higher and higher order.
So you say that gamma is 0 for most conformal classes is like enough for the Weyl curvature to be.
So the condition here actually is that all of your minimizing Yamabe metrics, so they're all going to be weakly stable in the sense of so their second variations will be non-negative. The second variation of the Yamabe energy will be non-negative. And if it is strictly, if all of them are integrable, meaning either the second variation is strictly positive, that's already true generically, or even if the second variation has degenerate directions, but that correspond to infinitesimal variations leading you to another minimizer, then you get quadratic growth. Then you get gamma equal to 0. So when you get gamma positive is when you have a non-integrable critical point, meaning the second variation has directions in its kernel that don't correspond to variations generating another critical point. So is it at all relevant that this particular family of examples are they're actually locally conformally flat? Is that typical of the? To be honest, the thing that I think is the most relevant about this family is that it's simple enough that you can really get your hands on it, because thanks to the symmetries of the situation, you can reduce this down to an ODE problem. Yes. For which you can actually, so, really fair example. Sorry? This is a very unusual example for the Yamabe problem. One actually can prove the solution has to be radial and. Right. And that's, in general, you can't expect to say, in general, you really can't expect to say anything explicit about these minimizers. So this is somehow a special example, but I would say to me what's more important than conformally flat is that this is is simple, say, and that you have this bifurcation in the ODE.
So the distance here is again a norm of U.
It's a
L21 norm of U plus.
W12 norm of U. Exactly. So okay, so how can we interpret this distance? So if you take your conformal metric G tilde to the original metric G with volume 1 and with almost minimal total scalar curvature, then it's close to some minimizing Yamabe metric in particular in a way that controls volumes of sets. So yeah, so it's closeness in W12 of the conformal factors. In particular, this says you take any set you like, just a set of points fixed. You measure its volume with respect to G tilde. You measure its volume with respect to G bar. And those measures are quantitatively close in terms of epsilon. Okay. So, okay, so I'll draw the interpretation to be this energy profile picture very quickly. The picture necessarily looks worse than the ones that we saw before for the following reason. So here on this two-dimensional axis, again, let's draw this infinite dimensional space of conformal metrics of volume 1. And here in red, I'll draw the minimizing Yamabe metrics. So unlike our previous two pictures where we could say, all right, the family of minimizers are explicit, they're all related by some symmetry, so we can really parameterize them by some k-dimensional Euclidean space. Here, they are what they are. As Claude was mentioning, I mean, somehow it's very unusual that we have an example where we can really write down the minimizers of this problem. And so this is somehow the main challenge here, is that we can't write these down. But so anyway, the picture is something like this for the energy profile. So even though they might look kind of bad, this class of minimizing Yamabe metrics, we get some explicit, some quantitative modulus of growth of the energy away from this class of minimizers. I think in this direction, but also I've tried to draw kind of in here. Also, we have some quantitative rate of growth. Okay, so in the last 3 minutes, let me say one or two words about the third setting that I was hoping to talk about, but I won't push my boundaries to see who walks out. So the third energy function I wanted to mention is the first eigenvalue of the Laplacian. So the physical problem that this corresponds to is what's known as the Faber-Cron inequality. So if we're looking at all drum heads of a fixed area, I think maybe you're designing a drum, you pay by the square foot for animal hide, so you're just using a fixed amount. And your goal is to find a drum that can produce the vibration with the lowest possible frequency. Then you want to take a circular drum. Okay, so this is the best shape of a drum head in terms of producing the vibration with the lowest frequency. Okay, mathematically, this is an optimization problem. So the objects now are going to be bounded open subsets omega in Euclidean space. Our energy functional is going to be the first eigenvalue of the Dirichlet Laplacian. What does that mean? So this is, by the way, okay, physically, this is the frequency of the lowest frequency vibration. It's the smallest number, lambda, for which we can find a solution to the following eigenvalue problem for the Laplace equation. So actually, I'm guessing a lot of people in this room do like the Laplacian, but if you don't like the Laplacian or you don't know the Laplacian, this is the same way that n by n matrices can have, right, they have eigenvalues and eigenvectors. The Laplacian is an operator that takes functions to functions, and it also has eigenvalues, and instead of eigenvectors, eigenfunctions. So lambda is the smallest eigenvalue. The corresponding eigenfunction here, we'll call it the first eigenfunction. Physically, this corresponds to the vibrational mode corresponding to this lowest frequency vibration. Okay, and so the minimization problem that this drumhead design problem corresponds to is we want to minimize the first eigenvalue of omega among all sets omega that have volume 1. And in any dimension, this is given by the first eigenvalue of a ball. Okay? And so now the stability question, we can sort of ask this in two directions. So if we have some set whose first eigenvalue is almost minimal, we can ask, is omega close to a ball in some geometrically meaningful sense? And we can also ask, is this corresponding vibrational mode on omega close to the one for the ball? Are these first eigenfunctions close? Okay, and the second question ends up being the one that's important in the applications that motivated our work. So a brief, okay, we prove the following quantitative stability estimate, which says that if you take a bounded open subset of Euclidean space normalized to have volume 1, then first eigenvalue is equal to that of the ball plus a little bit, then it's order epsilon to the power of 1. It's our usual quadratic growth. And the key point of this theorem is that the notion of distance that we consider, so the way that we're measuring the distance of omega to the nearest ball, is first in terms of the volume of the symmetric difference. This is like what we saw before for the isoperimetric problem. But additionally, difference between eigenfunctions, u omega and u of the ball, measured in an L2 interval sense. Okay, and now I don't want to go too far over, so I'll just say in a quick word, right, the reason that we set out to prove this and the motivation behind this quantitative control of the eigenfunctions is that this has application to studying the regularity of interfaces arising in free boundary problems. So we, in recent work, we prove a rectifiability and uniqueness of blow-ups theorem for a type of setting that arises in free boundary problems. Okay, but so with this, I will go ahead and wrap up. So thanks very much.